We're going to continue talking about enzymes and how they work and some of the properties and the enzyme kinetics and how they can be regulated by different types of activators and inhibitors. And here is just a diagram that's showing us the concentration of product versus time as time elapses. And really what we're interested in looking at is the effectiveness of an enzyme is really how fast we can make product versus how much time. So the change in product over time is going to tell us about the velocity, right? The velocity of the reaction, and that tells us something about enzyme kinetics. We can also discuss this in terms of a constant times the concentration of substrate. So the concentration of the substrate, if we don't have any substrate, none of this is going to happen. We can't make any product. So the substrate really dictates how much of the reaction, how quickly it can go. And this is based on a constant that's based on the amount of product we're creating over time. Each different chemical reaction, each different enzyme is going to have a different rate, and that's going to be represented by this K value here that when we're talking about rate constants. When we can graph these things out, right, over time or versus different concentrations of our substrate, so if we have a 0.05 molar or 0.1 or 0.2 molar reaction substrate, the amount of product we are able to make changes, and the more substrate, the more product we're able to make, the less substrate, the less product we're able to make. And there's a velocity, that's this velocity initial, velocity naught, V naught, based on the line that comes off of here from and it's actually the derivative of this line right at the 0 time point. So the initial velocity is going to be greater for a higher concentration, and this velocity is going to be lower and lower depending on the concentration, and we can graph that out. So the initial velocity times versus the concentration of substrate is going to increase with increasing amount of substrate. This helps us define that reaction rate constant, or K, that we mentioned up here, K times concentration of S. That is defined by the slope of this line, so the derivative of that line. When we have limiting substrate, that substrate is what actually dictates the rate of the chemical reaction. Again, we're looking at another reaction graph here. The rate on the y-axis, the substrate concentration with a constant enzyme amount, we have an increase in rate until it eventually maximizes out here. And so we have a straight line. If we have, again, excess substrate, if we increase the enzyme concentration with the excess substrate, we can actually increase the rate at a constant rate. And this makes sense if we look at this enzyme with Pac-Man, little Pac-Man enzymes, and their substrate, which is the Pac-Man pellets, where if we have one enzyme, these compounds are going to get eaten up at a certain amount of time, but if we have twice the amount of enzyme, we're going to be twice as fast to catalyze that reaction. And ultimately, these rates of reaction are controlled by how fast that enzyme is able to turn this over. But if there's, for example, 10 to the 8th collisions per second of enzyme with substrate, one of the most efficient and effective enzymes is called catalase. It processes hydrogen peroxide in our bodies to protect us from oxidative stress. 1 in 10 of those actually results in an enzymatic reaction. So that's one of the most efficient enzymes known to humans. Another graph looking at the concentration of the product over time, looking at 2 different concentrations of enzyme 1 and twice that concentration, we can see that that reaction rate, that initial slope for both of these is going to increase with increasing enzyme concentration, which should make sense. Now, if we're looking at these reaction rates, right, the rate over the substrate amount, we should be able to easily identify the maximum velocity. So Vmax is going to be about 3 moles per minute. So that means it's making 3 moles of compound of product per minute in this chemical reaction. We can graph these out, and there's some important things to identify and look at when looking at these, when we're graphing out the rate or the initial velocity versus the concentration of the substrate. And what we notice is that this line that's created when we make these different when we do these chemical analyses, is that it actually creates a rectangular hyperbola. That's very common for chemical compounds and enzyme kinetics for that type of reaction, and the kinetics to occur in that way. And this gives us the mathematical way that we can represent that is through this rectangular hyperbola equation, where y equals a over x, a times x over b plus x. And that corresponds to different values in here, including the maximum velocity, which we just talked about in the last slide, and the Km value, which is referred to as b in this upper equation, all based on the concentration of the substrate, right, as x. And the Km value, it's the Menton constant, and that's telling us about how well the enzyme has an affinity, the affinity for that substrate of the enzyme and the substrate affinity. And so that we can figure out the Km value by looking at Vmax, finding half Vmax, and looking over at where that intercept is for that line and going down, and that's the Km value. And that's where essentially half of the enzyme pockets are bound by substrate. That's where half of the enzyme pocket is bound by substrate. The lower the number, the lower the concentration of substrate, the better affinity for the enzyme. Okay, great. So this enzyme kinetic matches the equation for rectangular hyperbola, but it's not really that practical for in practice looking at, well, what is the Km value, or what is the Vmax, or what kind of, and in the future we're actually going to look at what about inhibitors? What do inhibitors do to this, and how can we figure out if it's an inhibitor, what kind of inhibitor it is? So Lineweaver-Burke is a type of transformation that we can do to this data, where we basically take the inverse 1 over V naught and versus 1 over the concentration of the substrate. And when we plot this out, what we actually get is that value at the y-intercept is going to actually equal 1 over the Vmax value. And the x-intercept is actually going to be the inverse, the negative 1 over the substrate, the Km value. Now, this might not make a lot of sense right now why we will do this. It will make more sense once we start looking at what happens with inhibitors and what these equations and these lines look like once we start looking at the inhibitors to different enzymes. So here's the Lineweaver-Burke equation, and this actually gives us the equation of a line. So 1 over V naught, so y equals mx plus b, right? This is the equation of the line, and these different components are what we're actually graphing out, and this is how it all works. So if we get the slope, right, that is going to be equal the Km value over Vmax. If we get the y-intercept, that's going to be 1 over Vmax. So we can use all of this information to solve Vmax and Km values as well. And it's easier to graph a line than it is to graph a rectangular hyperbola and solve these constants. That is what we do. It's a little easier and to work with this type of this reaction, and we can graph this in Excel easily. More people can handle this data a little easier. Before we use that Lineweaver-Burke transformation to start to look at and examine different types of inhibition and activation, we're going to talk about the different types of inhibition. There are different ways that we can do this. We can have feedback and allosteric control. There are two different strategies. We're going to talk about both of them. And we can have activation, or we can have inhibition. And a lot of times we'll draw, if there's a chemical reaction, we'll draw an arrow. Sorry, I don't know why that was black. We'll draw an arrow that says that it's activating. If we're going to inhibit something, we draw kind of a straight line up and down to say, well, that's an inhibition reaction. So you'll notice that straight line is right here. We have that kind of line with the end block. We're saying, here's an example of feedback inhibition. And if we have a chemical reaction where we have substrate A is bound by some enzyme and it turns into B, and then there's another enzyme and we have C, and so forth. But B can also be sidetracked into X, Y, and Z reaction mechanism as well. And each of these arrows is a different chemical reaction and presumably catalyzed by a different enzyme. Now, if we go from A to B and then B starts to go down here and make Z, if we make a lot of this compound, Z, it actually comes up and it can inhibit this enzyme from making more X, Y, and Z. So this is a way that we can have feedback inhibition. That formation of a final product actually goes upstream and inhibits an enzyme upstream of it. You can here's an example of aspartate, aspartyl phosphate, semialdehyde, homoserine, right? You can see that once we make all of these different amino acids, some of these can come back and feedback and inhibit different processing of aspartate into these further down amino acids. So as soon as we have plenty of isoleucine, that creation of isoleucine actually goes upstream and blocks the conversion of threonine to isoleucine, methionine, right? We're going to keep homoserine from making more of it. So there's a feedback inhibition. Once we have abundant enough product, that can sometimes come back and feedback and inhibit an enzyme. Kind of a lot of those things I see sometimes on the internet where we're looking at which glass gets full first, and you have all these little glasses, and it kind of it's all about kind of feeding back and closing up these little holes for these compounds to work through. We have different types of inhibitors: competitive, uncompetitive, non-competitive, and mixed inhibition. We're going to talk about all of these different types of inhibition. So classic competitive inhibition is where that substrate is going to be inhibited. It's a direct competition for that active site. So you can see here is your enzyme, and normally it's going to interact with a substrate, but that inhibitor binds to that same spot and it's competing for it. So it cannot work the same way. And now if we go back to that Lineweaver-Burke plot, we can actually see what happens when we add competitive inhibitor. And so we can see this normal line under the without any inhibitor, and with increasing concentrations of inhibitor, this line gets more straight up and down. Well, let's make sense of this, right? So if I have, for example, let's just say for simplicity's sake, if I have this Km value right here is 1 over 1 versus right here is 1 over 2 versus right here is 1 over 3. Right, as we get, this is 1 over 1 is 1, this is at 0.5, this is 0.3 repeating, right? So we're getting smaller as we go here. What does that mean for the Km value, right? We have 1, 2, 3. Since it's in inverse of that, that Km value is actually getting bigger and bigger and bigger as we go over here and here and here. That's telling us that we think it's an apparent Km value. That Km, it looks like with an inhibitor that enzyme is getting less and less effective, right? This Km value is getting bigger and bigger and bigger. It's getting less and less effective at binding that substrate. And that's because we have an inhibitor directly inhibiting the binding of the substrate. So it makes sense that that Km value is getting smaller. The Vmax doesn't change though. If we are able to add enough substrate, we're able to overcome any of that inhibitor that is there because it just overpopulates and it doesn't matter how much inhibitor is there. So again, Lineweaver-Burke plot helps us to figure out what type. So a competitive inhibitor, this is what a typical competitive inhibitor is going to look like. We can just add an inhibitor, and if it looks like this, if we have this Vmax that stays the same and Km value, apparent Km value changes, that tells us that it's probably competitive inhibition. Now, if we look at uncompetitive inhibition, uncompetitive, so if we have the regular substrate and we have, or the enzyme, and the substrate binds in the binding pocket. Now there's another different binding pocket for the inhibitor that's separate and unique and different from that substrate. So the enzyme substrate complex is able to form, but is not able to finally make a conversion to a product. So the inhibitor only blocks the enzyme substrate complex, not just the enzyme complex alone. Now you'll notice that this is different than the previous version. We see that these are parallel lines now instead of converging at the y-intercept here. So the Km value, the parent Km value, actually is going to be getting better. It looks like it's binding better, but the Vmax is getting lower and lower. So the Vmax goes down during this inhibition process. So there's no way we can't increase the substrate concentration to outcompete the inhibitor because it's binding at a different site on the enzyme. So to look at this, let's just look at the control example. If we have a Km, a negative Km value equals -2, right? That apparent Km would be 0.5. So that would be for the control. Now, if we get to a more negative number, the negative Km equals -4. That gives us a 0.25, and then this Km value 0.167. So this Km value with this uncompetitive inhibitor, it looks like the binding efficiency is going down, but we're also changing. The Vmax is also changing while we're doing this. So the increased inhibitor, it looks like the apparent Km value is decreasing, which would suggest that the binding is getting better, but we're adding an inhibitor, so that doesn't really make any sense. If we look at a non-competitive inhibitor, that's where the inhibitor can bind to either the substrate enzyme complex or just the enzyme complex alone. So it can do both of these and eventually block the completion of the reaction. Now this changes where now the Km value appears to never change. So this 1/Km value is always the same. It intercepts at the y-intercept. But now the Vmax, that looks like that it changes. So the Km remains constant while the Vmax can change. It's kind of a weird situation. It's basically where, see if we have the Vmax is 1, and then we can go to half of Vmax is 0.5. And the Km value is here, versus if we reduce the Vmax equally and it's to 0.5, then we go to 0.25, it's the same. So the enzyme, the Km value actually, regardless of if it's inhibited or uninhibited, it ends up being the same. So it's kind of a weird combination that happens here. It seems weird that you can have that, but it's able to happen. It's possible, as you can see here. So this is how we can use the Lineweaver-Burke plot to figure out if it's competitive, uncompetitive, or non-competitive, and these are the results. Looks like it raises the apparent Km value, but Vmax remains unchanged for competitive. Uncompetitive means that it lowers the Vmax and Km, but the ratio of those two remains unchanged because we have those parallel lines that are happening. And then the non-competitive lowers the Vmax, but the Km appears unchanged. Why do we care? What does that matter? Who cares if it's competitive, non-competitive, uncompetitive? Well, it helps us to understand how an enzyme's working, and it helps pharmaceutical companies develop useful drugs. If it's a competitive inhibitor, or if we know something is acting as a competitive inhibitor, we know it's acting in the binding site. If it's non-competitive or uncompetitive, it's got to be binding somewhere else. It's not the active site. It's some other allosteric site, and that allosteric is that vocab word that basically means it's a site that is outside the enzyme active site that influences enzyme kinetics. So they can use this Km data and Vmax data to fine-tune drugs and see which drugs inhibit the best, which ones are changing the activity of that enzyme reaction the most. So let's look closer at allosteric regulation. Again, it leads to binding to the protein that leads to structural changes that influences that enzyme function. So it changes where the active site, maybe how the active site is organized or the fluidity of the molecule. They don't exhibit normal Michaelis-Menten kinetics, as I showed you previously, because of that change in the function. A lot of allosteric enzymes can change, are modified by normal metabolic inhibitors and activators. So you can have allosteric components that actually inhibit and activate it, make it more effective and more efficient as well. So a lot of times these work as more sigmoidal curves rather than hyperbolic. So this is an example of a sigmoidal curve where there's this kind of exponential growth and then it kind of fades off, and still we get this maximum velocity eventually. But we've got this increase, a drastic increase at a certain concentration of substrate that increases how it's working. Here's an example of these are where we have tensed. This is kind of two different terms. T versus is the tensed form of the enzyme, and R is the relaxed form. And so the R form is relaxed and it's able to actually work more effectively and efficiently. The tensed form works less effectively and efficiently. So with really low substrate concentration, we get really low velocity of reaction because these tense forms don't work very effectively. Once one of these enzymes is bound by substrate, however, we get the relaxed form, and then we can start kind of increasing the reaction rate. So this actually makes everything work a little better. And this being bound helps to induce kind of, you see how this kind of changes the shape. It's not completely. The things that are touching it to the sides, they work a little more effectively. And if we have two bound, we have all. These are really relaxed and helping to influence these. So as we kind of change the bound state of this, the more that are bound, the more effective they are. And that's why the increase of the reaction rate when they're all bound. So not only the sites that are catalytically active are increased their efficiency, but the adjacent and associated proteins can be as well. So here's an example of another type of allosteric. Many times they're non-covalent interactions that can change the shape. So intermolecular forces that can come in and regulate this. So this is the enzyme. Here we have the substrate up here and the allosteric site, and here's the active site here. So normally we have the allosteric regulation. We have a normal chemical reaction under normal conditions. We have the enzyme and substrate bind and react chemically. But here we might have the allosteric site on a different region that might change the shape of the active site and allow the substrate not to bind. So here's a negative regulation that can occur. When we're looking at cooperative binding, something more with hemoglobin and oxygen binding, we can kind of see these changes over time when we have activators versus inhibitors. And we see this more when we have activators, we have more of a hyperbolic binding, and then the sigmoidal binding under normal condition, even more enhanced or changed sigmoidal binding when we have an inhibitor present. So Vmax ultimately with these types of reactions are going to be the same, regardless of if it's inhibited or activated, but the Km value will change. You can see half of Vmax, right? As we inhibit it, it's going to go to the right. That means the Km value is increasing. That means it's less effective. It's less effective at binding. The activator is going to give us a more hyperbolic and a better apparent Km, whereas an inhibitor is going to give us a larger number Km and a worse Km. Here's an example of allosteric enzyme regulation in glucose metabolism. So when we get fructose 6-phosphate is one of those compounds that we're going to see in the future when we start looking at glucose metabolism. We have phosphofructokinase 1 is the enzyme, and it's going to use ATP and this phosphofructokinase as the substrates for this chemical reaction. We're actually going to phosphorylate this. We're going to replace this alcohol group with a phosphate group. That's actually going to then go downstream, and eventually we're going to get phosphoenol pyruvate, which is shown here. The production of a lot of this phosphoenol pyruvate will actually come in and bind to phosphofructokinase 1 in an allosteric site, and it binds and changes the effectiveness of this chemical reaction. When there's not this present, ADP is actually able to bind this phosphofructokinase 1, and it increases the speed at which this happens so we can make more of the phosphoenol pyruvate. So these are the two possibilities where we have this phosphoenol pyruvate inhibiting this enzyme, and then the other option is if we have high amounts of ADP, low amounts of ATP, right? We can actually increase the activity of this chemical reaction, and it helps to regulate the manipulation of where we have different metabolites in our bodies. So here's where we would have the phosphoenol pyruvate that would be inhibiting that reaction. The phosphofructokinase, this is the enzyme, right? Normal state, it would be this way. With the phosphoenol pyruvate, we'd be here. And then with the ADP, that would actually activate that chemical reaction. And that makes sense, again, because if we have really low amounts of energy, which would mean we have high ADP, essentially low ATP concentrations, we want to increase this chemical reaction to undergo the breakdown of glycolysis and the formation and creation of more energy. When we're really energy dense and we have a lot of ATP and low ADP concentrations and maybe a lot of phosphoenol pyruvate, that would say that we've probably processed a lot of sugar and we have a lot of energy. And so we don't need more, so we can block this and help form the processing of these larger groups into glycogen stores and fat storage. Here's another example of allosteric regulation, the next active site where phosphorylation actually can activate that. So we have a covalent modification here on these regulatory sites. We can bind CTP or phosphorylation that can change how the structure of this enzyme looks like, and it changes their ability to function properly. So just another example of this. This is kind of an idea of metabolic channeling, when the product of one reaction is transferred directly into the active site of the next. And we can see this on ribosomes, do this frequently, where we have the binding of the transfer RNA is pushed into the next enzyme, and then we have this other group here. So we kind of channel this from one component to another. The book, I think, gives us an example of tryptophan synthase, but I think the ribosome seems like the perfect example for this type of activity. Some inhibition can be very detrimental for a protein or an enzyme and can be irreversible. And so this is an example of heavy metal ions can lead to the binding of active sites and the permanent activity defects that can be caused there, where basically the only way to change that is to completely recycle the entire protein and make a new one. Other types of drug classes have been identified and used. An example of is the angiotensin 1 is a precursor to angiotensin 2, and angiotensin 2 is important for elevating blood pressure and causing the contraction of blood vessels. But the American pit viper has a component that actually acts as an ACE inhibitor, which is an enzyme or an inhibitor that blocks that conversion from angiotensin 1 to 2. A similar drug has been made, modified captopril, that looks a lot like that ACE inhibitor to help lower blood pressure in people. So this is where I'm going to stop here for these videos, and we'll continue talking about cofactors and coenzymes in the next set of slides.